Hello, welcome to Picture Me Coding with Erik Aker and Mike Mull. Mike, I have a new mic.
I see that. It's lovely.
It's hopefully you can hear me a little clearer, but maybe it's exactly the same. And I've just been duped by that microphone industry.
Yeah, it's kind of hard to resist big microphone.
Maybe being on a podcast makes you an amateur audio engineer, just like going surfing makes you an amateur meteorologist and oceanographer. It's fun being a neophyte, an amateur, not knowing things.
I was just thinking to myself that I need some more nerdy hobbies. I was out hiking yesterday and I got into a 20-minute conversation with some guys doing ham radio. And I thought, maybe I should do ham radio. And then I thought, no, I'm already a bird watcher and a podcaster. I will probably explode if I get another nerd hobby.
Okay, so a little bit prejudicial. How old were these people you were talking to ham radio about, do you think? What would you guess? The decade of life they're in?
I would guess they were very similar to my own age, which means old, extremely old.
Okay, so that fits my expectation with ham radio.
Yeah, me too.
Speaking of audio engineering, what have you been listening to?
This is the time of year when people start putting out their best of the year lists, which I think is unfortunate because it seems like we should count December as well. But I guess people do it because they get more traction on their like affiliate links and stuff like that.
They get more likes and shares and subscribe button smashing?
Yes, important extra smashing.
Internet tokens that mean something to somebody.
So I have a hard time resisting them. I'm not sure why. I think lists of things are probably pointless and they tend to have, 90% of the same stuff on all of them. But you do occasionally find some things that you missed and that are kind of interesting. And one of them that I came across and have been listening to a lot this last week is an album called The Mesthetics and James Brandon Lewis.
Oh, never heard of that. What is that?
So it's actually two artists. One is The Mesthetics, and the other is James Brandon Lewis, who's a pretty well-known jazz saxophonist.
Oh.
The Mesthetics is a three-person band, two of whom are the former rhythm section of Fugazi.
Oh, bass and drums. Former rhythm section? Did Fugazi break up? They've always had the same lineup of people, I thought.
Yeah, I don't know if they broke up or not. I haven't heard a new Fugazi album for a while, so I'm assuming they're in retirement. But anyway, I don't know how these two somewhat different artists got together, but they put out this album together, and it's kind of what you would expect it to be, given the description. It's
I don't know what to expect. It's a jazz album with two guys from Fugazi.
Yeah, it's a jazz album that's got a pretty good groove to it. There's a fair bit of variety here, but if you don't like your jazz with a little bit of guitar in it, then it may not be for you. But I've been enjoying it. It's got some tracks that sound like Fugazi with a guy playing saxophone. But it's also got some pretty nice jazz pieces and just interesting. It's all instrumental as you would expect. But
it sounds like a good holiday album. You're in the mall, you're shopping. This is on in the background. There's that nutmeg and cinnamon scented fragrances in the air. You got your bags.
Yeah. It's pretty much like Perry Como for the modern era.
What's the guy? Bublé. Bublé comes on in my house when my wife is wrapping gifts. I've been listening to an album called Primordial by a band called Telekinetic Yeti. They're from Dubuque, Iowa. You like that name? I like that name too. Yeah. Many years ago, we played Rock Band over the holidays with my whole family, and our rock band name was Puke Wizard. I came up with that, and I always wanted to have a band called Puke Wizard. I think that's a great name. But actually, this band from Dubuque, Iowa, they play straight up stoner doom. They have a song called Ancient Nug, and a song called Stoned Ape Theory, and another one called Toke Wizard, which is similar to my Puke Wizard idea. But Toke Wizard's a rad song, actually. So I realized something bringing this to you this week. I was like, oh no, this is another one of those, like, here's an album that you could just put on and fade out of society too. I tend to talk a lot about stoner music, it seems.
It's interesting. We talk about stoner music a lot. We listen to a lot of stoner music. We've gone to concerts with prominent stoner doom bands, and yet neither of us are really stoners.
Yeah, it's like I would probably go to a convention for this music. It's funny for someone, no judgments, who doesn't really partake of it. Someone who doesn't know me would probably assume some things. I think I have an appreciation for that culture, that stoner culture, stoner doom at least.
What's that great YouTube documentary that's on YouTube?
Such hawks, such hounds.
Such hawks, such hounds. Yeah,
yeah. Definitely. That's that. When sometimes the riff just hits you in the gut, and you gotta play it for 45 minutes straight. It's a beautiful moment. Beautiful moment in the history of the culture. So here's my thing. Telekinetic Yeti, if you want to get your feet wet in the genre and you don't want to listen to a song that's an hour long because it's like too big of a commitment or something, you should check out this record, Primordial. Start with the song Toke Wizard, put it on, and let all of your concerns just float away. That's my suggestion for the holiday.
I'm going to do that right after this.
So, Mike, it is now December. December for me, oddly, is compiler season. And it's not, I don't know, every single year around this time of year, for some reason, I start thinking about interpreters and compilers. Some years it's Advent of Code. I'm not doing that this year, but some years it is because of Advent of Code. Other years, one year someone gave me a book, writing a compiler, writing an interpreter in Go is the name of the book. That's a fun book to read. I liked reading it. I got that in December. It just seems every single year, December, boom, time for compilers. And you came to me this week with a topic. And at first I was like, oh, I don't know about this. I've never heard of this person. And immediately I was like, oh, this is awesome. I am into this. So tell me your topic this week. Tell me what you want to talk about and why.
So this is another one in our series of standing on the shoulders of giants. And our giant for this week is Frances Allen,
Frances Allen, I'd never heard of her.
Yeah, she is not well known, which is unfortunate. I suppose in her field, she is probably very well known. But among other things, she was the first woman to win the Turing Prize. And her work has primarily been on compiler optimization and, mostly working for IBM. And I confess this is not something I know very much about. I've seen the effects of it over the years. If you've written code in a compiled language, C or Fortran or something like that, you've probably experienced, dead code elimination, where you're writing some sort of hack to test something, and then you run it with optimization on, and it completely eliminates that code, and suddenly your program is very fast. Mm-hmm. Because that loop that doesn't do anything is gone now. I remember on my very first code interview, or my very first interview for a software engineering job, one of the questions was, why do programs sometimes stop working when you run the optimization? So
wow, interesting question. So you might think compiler optimization, that doesn't sound so exciting. This stuff is rad. If you've never worked on an interpreter or compiler, I think for me, a lot of the fascination comes out of the fact that I'm often writing programs that have to deal with strings. And so that's what we start with. I write a lot of junk over strings. And all of these compilers and interpreters are starting with, you might use bytes, but it's like I've got a sequence of characters that is a programming language, and I want to do something with that. I want to transmute it into this machine level lower language. I want to compile it. Or I want to take a language, maybe a DSL, something, and figure out how to evaluate it. So I've got a string and I want to turn it into a working program. And it's actually pretty fun trying to do that. I'm going to iterate over the characters. I'm going to try to turn those characters into tokens. Once I have tokens, I'm going to try to build a graph out of it. So you start simple. You start with just a program that just starts reading strings, and you get very quickly into all this really interesting theory. I've got a abstract syntax tree. I've got maybe semantic analysis. And then you start getting into what Francis Allen contributed. I maybe start running optimizations over these things. And then it goes even further. Now, I have to admit, Mike, when I start thinking about compilers, the part that interests me is it's often people describe compilers as broken up into front end, middle, or middle end. Sometimes you hear middle end, which I think is a funny oxymoron. It doesn't really end if it's in the middle. Anyway, so front end, middle end, and back end. And as soon as we get to back end, I have to tell you, my interest kind of falls off a cliff.
I think I'm kind of the opposite.
Okay, good. So together we will shake hands. It's like in Predator. I will be the front end, you be the back end, and I'll just hand it over to you.
When I started out in the business back in the days of the dinosaurs, it was actually pretty common that, if you wanted to make something super efficient, you'd drop into assembly language. And like even early C compilers, probably even now had an ability to like inline assembly language code so that you could incorporate that into your C program. And I think now we've kind of reached the point where general advice is, unless you really, really, really know what you're doing and understand the hardware well, the optimizers kind of do it better than you do.
Mm-hmm.
So
let's talk a little bit about Frances Allen, a little bit of biography. She was born in 1932. That's the same year my grandfather was born. Her birthday, August 4th, and she actually died on her birthday at age 88 in the year 2020. She died of Alzheimer's disease. She was profiled all over the place when she passed away. She was profiled in the New York Times, Verge, CNN, IEEE. You sent me an interview with her from the ACM, and I really liked this interview. We'll include a link to it here. So she started at IBM in 1957. I just want to give you a little bit of some of the lines from that interview when she talked about how she started there. When I joined IBM, this is from her interview, this is what she's saying. In 1957, I had a master's degree in mathematics from the University of Michigan, where I had gone to get a teaching certificate to teach high school math. But I had worked on an IBM 650 there, so I was hired by IBM Research as a programmer. So this is already interesting. It's like this person never intended to go into the field. She had a master's degree. Goal is to teach high school math. And this is like, hey, I'll take this summer job at IBM.
Yeah, it's very possible that at that point in time, most people didn't even know that was a job. So,
yeah, it's true. Yeah. So she goes on, my first assignment was to teach Fortran, she says, which had come out in spring of that year. And the interviewer, the question asked her this question: did you already know Fortran, or were you learning it a week ahead, as professors often do? And she says, yeah, a week ahead. They had to get their scientists and researchers to use it if they were going to convince customers to use Fortran. I had a pretty unhappy class because they knew they could do better than any high-level language could. And the interviewer says, did you win them over? And again, she's trying to convince them to use Fortran. Yeah, and they're like, no. I want to write assembly. Are you crazy? This is too high level, Fortran. And she says, yes, I won myself over too. John Backus, who led the Fortran project, sidebar, John Backus created Fortran, right? He had set two goals from the beginning: programmer productivity and application performance. I learned all about the compiler as part of teaching this course. And then finally, the interviewer asks, did you ever work on that compiler yourself? And she says, this is the part I loved, I was reading the code in order to do the training. It set the way I thought about compilers. It had a parser, an optimizer, register allocator. The optimizer identified loops, and they built control flow graphs. So just to sum up, she gets a job at IBM, 1957, and they're like, oh, you've worked on an IBM before. We're going to hire you as a programmer, and you have to teach people here at IBM, scientists and research, you got to teach them how to write Fortran. And they're not interested in writing Fortran. And she's like, okay, I guess I'll read the Fortran compiler so I can teach them how to write Fortran. I just thought this was so cool.
Yeah, that's seems to be a theme of her career. And one of the reasons I really love the work that she did is that she did some pretty, like if you read her papers, they're pretty mathematical, but she also like sat down and wrote code. There's like code listings in some of her papers. So she was definitely a practitioner too.
So there were a little bit more about her background. There's a profile of her in the ACM, and she got interested in compilers from reading the Fortran compiler source code. She called it a throwaway job, and she ended up staying at IBM for 45 years. And she was their first female IBM fellow in 1989. And then ACM writes, in a field long dominated by men, Miss Allen was a force for change. In the 70s and 80s, thanks largely to her own efforts, women accounted for half of the experimental compiler group inside IBM. This is a quote from someone who worked alongside her. One of the many things Fran did was attract women to her field, said Gian Ferrante, who worked alongside Miss Allen for more than a decade. She looked out for people who were underrepresented. So she worked on compilers. She then later on, towards the end of the 70s, 80s, started working on parallel computing to automatically parallelize computations. This is pretty cool stuff. So we got Fortran and compilers, compiler theory, and then automatically parallelizing computations. I was blown away by this. I had never heard of Frances Allen again. I was like, wow, this is pretty cool work.
Yeah, it's really amazing. And I guess it's just something that we kind of take for granted. And, if you're a journeyman programmer and not somebody who works on compilers, it's there and it makes your life better, but you don't really delve into it too deeply.
Mm-hmm. So if you look at her Wikipedia entry, there's a handful of papers that are referenced there as her like notable papers. And if you look at the ACM, they talk about that too. There are three really that I think we wanted to talk about today. Her first paper was just called Program Optimization. It was published in 1966 as like an internal note at IBM. So you can't actually find this paper. I couldn't find it. It got later republished in a journal in 1969. And I couldn't, I think I need a paid academic subscription to be able to access this paper. So the first one I read was called Control Flow Analysis. I really liked this paper, Control Flow Analysis. I liked it far more than I thought I was going to like it. It was published in 1970. The version I found online is like a scanned typewritten copy. Not that fun to read. I honestly think this paper, Control Flow Analysis by Frances Allen from 1970, I think it's going to end up becoming one of my favorite papers I've ever read. I was blown away by this paper.
It's got some very surprising stuff in it, and it's interesting and stuff that I really had no clue about. So
yeah, me too. I mean, I think I knew vaguely about some of these compiler optimizations. I mean, I have heard of an abstract syntax tree or an AST before. So here's what the paper talks about. There's 5 sections in the paper. The first section is about graph data structures in general, and then you get graphs with respect to compilers. That's the first section. Then the second section introduces this thing called dominance relationships. Now, the paper didn't invent that. That existed before. And the third section is intervals. So the idea of a dominance relation is you might have a node in the graph that you have to go through before you can visit successive nodes. We'll talk about how you build a graph out of a program in a second. And then the idea of intervals is you can actually cut the graph. And why would you want to do that? Well, the interesting thing is once you partition a graph, this is the fourth section of the paper, you now have the opportunity to analyze it. And just a hint of what that means. If I have maybe some code, and inside the code, there's a for loop, and it loops over some massive data structure. And inside that for loop, there's like assignment to a variable that doesn't have anything to do with my looping. I'm assigning to that variable on every iteration through the for loop. That's pretty wasteful. By analyzing the program, using a graph, knowing how things relate to each other in the graph, we can actually optimize how that program is really run, how it's compiled and how it's run. This stuff is pretty cool, I thought.
very cool.
So the paper says, you do this analysis, this control flow analysis, and you can actually start asking questions like, where is this variable referenced? Is this an inner loop? Can we move this variable declaration out of the loop?
One of the things I struggled with these papers, they're fairly readable if you scrutinize them, but they don't necessarily talk about how this relates directly to program optimization. So some cases they do, but like for instance in the section about dominators, back dominators, and she specifically says if you want to know how this relates to program optimization, go read this other paper.
Yeah,
So,
there is a little bit of a draw the rest of the owl to this.
yeah.
Especially, so we're going to talk about 3 papers. I think maybe we won't get to the last one. The first one's called Control Flow Analysis, 1970. The second one's called A Catalog of Optimizing Transformations. That's 1971. And the third one, 1976, is called A Program Data Flow Analysis Procedure. So these are the famous programs. So control flow analysis, what I started with here. And the first part of the paper starts talking about how you've got directed connected graphs, right? So some basic graph theory. You might have circuits like a loop where you end up on the same node you started in. You can have a simple circuit where you've got like a simple loop, or it can get a little more complicated. They call that a composite circuit. And we can describe this graph as a control flow graph if I've got nodes, which are, she uses the word blocks, right? Like you think of a block of programming code, right? And the block has one entry point and one exit point. And so another funny thing happened to me when I was reading this is like it felt really intuitive reading what she was describing, because she's talking about, I want to represent this program as a graph. And I kept thinking about Dijkstra and structured programming, and I've got a single entry point, a single exit. And I want to actually write code that's easy to understand. And somehow if I do that, I'll end up writing code that's easier to represent as a graph. So it's almost like a graph is in the background of my ability to think about what's happening in code. If I start here, I evaluate this line, where do I go to next?
Yeah, I think it's a pretty intuitive way to think about the structure of code. It does not, none of these papers go into great detail on how these blocks are constituted. I think it's also fairly clear, since if you think of the structure of a program, you can sort of see the blocks of code, especially if you're thinking about something like Fortran.
Mm-hmm.
But they don't actually talk in these papers about how the nodes map onto the blocks explicitly, I don't think.
Well, there is kind of an algorithm suggested by control flow analysis. We can get to that in a second. So again, a block it's a linear sequence of program instructions. This is a quote from the paper, having one entry point, the very first instruction executed, and one exit point, the last instruction executed. So think of it a block, right? Program entry blocks may not have predecessors. They may be the start of the program, right? Predecessor. And the ones that terminate the program may not have successors. So you might have one entry point, one exit point for the whole program, and then you may have a bunch of blocks inside the program where you've got a clear starting point and a clear exit point. And a control flow graph is really the blocks and the control flow paths. If this, go to that block. If that, go to that block, right? And then she gets to dominance relations. So back dominators, forward dominators. If you can look at your blocks as a graph, you can say, okay, this node in the graph near the bottom, if it's sort of top down, you can kind of visualize a graph in your head, an arbitrary graph. This node at the bottom, every single evaluation of the program may get to this node. Maybe it's node number 6. And every time you get to that node, you will have had to get through node 2. Now, maybe there's some if this, go off in this other branching flow. If that, go off in this other branching flow. They will converge to node 6. And to get to node 6, they will have to have gone through node 2. And so node 2 is a dominator, right? It's the immediate back dominator of node 6. I'm like, okay, I can kind of see that's valuable. When you think about refactoring programs, we use these kinds of intuitions, like, oh, if I change how this function works, what is it going to break? Like, you have to have this stuff in your mind. I think that's why it felt so intuitive to me when I was reading it.
I went off and read the paper that she refers to in relation to how code optimization uses this domination idea. So just as an example, one of the things I gleaned from the paper is that this method is used in what they call common sub-expression elimination.
Mm.
This is a fairly well-known compiler optimization. Chances are, if you've used a compiler, you've seen this. But the idea is that you may have written the code not intentionally, but just because you're a human being, you may have written the code so that you're computing the same thing twice in different places. And because are able to figure out this structure of the code, they're able to eliminate those redundant computations and put them into one place.
Yeah.
Which clearly is going to take fewer instructions and make your program faster.
Well, I want to talk about intervals because I think that relates. So the next section of this paper, after talking about these dominators, talks about intervals. Now, she does say in the later interview with ACM, this is in the 2000s, she says that this work on intervals was all kind of obviate or made a little bit obsolete by, or superseded, I guess, superseded by minimum spanning trees and cut points and graphs. But the idea is related, right? Like, if I can identify an interval, this is section 3 and 4, then I can partition. So what's an interval? The idea is if I go through my graph, I want to find the back dominators that are the single predecessor.
I took away from intervals the idea that an important part of it is that you end up partitioning the whole graph. So once you've constructed this full set of intervals, one, they are disjoint, so intervals don't overlap.
Mm-hmm, mm-hmm.
And two, they constitute the whole graph. So it gives you this ability to sort of think of them as isolated pieces.
So I made a simple Python script to try to calculate intervals just so that I could understand it a little better. And the idea is as you traverse the graph, you look for these nodes that have where you haven't seen the predecessors before, if it's got other predecessors, and then those become, if they have like predecessors you haven't treated before, those become interval head points. And then everything below them should have that interval head point as its predecessor. So you can sort of say, what's the start of all of the key moments in this graph? You can kind of almost imagine a city with bridges connecting it. And you could say, what bridges could I destroy to completely isolate sections of the city?
I like that.
A little bit destructive. So we partition the graphs. Why is that cool? Once we can identify these intervals, we can actually reduce each interval to the head node. And why would we do that? We can now analyze the whole program. And so it says in the paper, this is a quote, information of global interest is left at the interval head and at the exits. And I was like, yes, this is like exactly what I feel like I'm thinking about when I'm refactoring. Let's say I've got some massive amount of code. I look at Python a lot, so maybe it's a Python module, right? It's thousands of lines of Python. I've got some function in there. I want to know who calls this function. Does the function modify things that are maybe shared with other things? Or does it have a single obvious entry point and a single obvious exit point? What is the, quote, global interest? If there are things that are just calling this function and getting the output and the function doesn't actually modify globally available things, then I could sort of do whatever I want in that function as long as the behavior is preserved, right? If I can identify using this graph structure information of global interest, it's actually pretty powerful. And the paper says when you do this analysis, global interest is at the beginning of the interval and the end of the interval. So this really seems related to human cognition limits to me. She says you can reduce programs in this way, and therefore programs are reducible. And then you have a lot of freedom to start optimizing it. And they did some analysis of the Fortran programs that were being written at IBM and that their customers were writing. And they found that 90% of the Fortran programs they encountered were reducible in this way.
Yeah, one of the things that I didn't pick up on at first, and I'm still a little fuzzy on, is that you can sort of repeat this process. So you can look at the graph and you can find a set of intervals, and then you can take the interval and reduce that to a node, and you can kind of repeat the process then, and you
Hmm.
if a program is reducible, it will end up essentially as a single node.
I really like gravitated towards this. It just like hit me, and I was like, yeah, I really, really like it. It made a lot of sense when I read this paper. I really liked this paper a lot. I don't know if that's coming through in my describing of it.
Yeah, it is. It's not a breezy read, but it's very enlightening.
It just felt like it made so much sense. I feel like every time I read some piece of code, I'm trying to figure out where is the information in this chunk of code made available to the entire program. I feel like that I'm trying to do that always. Where is this value used? If I can isolate a subroutine to a whole bunch of local variables, I use the word subroutine. Sorry, it's the 70s working its magic on me. I know that I could rename all those things and it has no effect on the whole program. And so this paper describes the graph structures and operations that you can use for a compiler to do that work automatically in some way.
I saw that interview also where it mentions that intervals were to some extent obviated by this spanning tree algorithm that was discovered by Robert Tarjan, if that's how you pronounce his name. But I was looking at LLVM, and LLVM has this whole set of optimizer passes, and one of them, there's still one in there to calculate intervals. So I think it is for some reason still used in program optimization.
So that's the control flow analysis paper. I thought it was a super cool paper. I did have a gist where I was hacking up some code to try to build intervals for a graph, not doing any lexing, parsing, syntax tree stuff, just pure graph stuff, just to try to understand how they build these intervals. So the paper ultimately says, look, if you build this data structure, you then have the opportunity to perform this control flow analysis. And that control flow analysis, super cool, super useful if you want to do optimizations. And so then there's this paper from 1976. This paper is funny because it's like, here's 20 or 30 compiler optimizations that we use at IBM. And it's almost like a listicle, like top 10 favorite ice cream drinks. It'll be like, here's a paragraph on loop transformations. And it doesn't tell you this is how you do it. It just says, oh, you can do this.
Yeah, it's a very useful paper though, because like I said before, the earlier papers talk a lot about these techniques for doing this static analysis, but it doesn't always make it clear how those are used in the actual code optimization. So it's nice having this separate catalog of code optimizations so you can sort of get a feel for how that stuff's being used.
I think this paper is easy to read, not so easy to understand. I want to give you a couple little moments from it. At the beginning, they write, a result of the recent work in optimization has been to systematize the potpourri of optimizing transformations that a compiler can make to a program. This paper catalogs many of those transformations. And the paper really is a catalog. It's like you're thumbing through, like, whoa, what was the one that they mentioned on page 12? Oh, yeah, dead code elimination. Got it. Like you don't need to read all the stuff beforehand to just look up that one. So the paper says at the very beginning, it's not obvious to programmatically determine what is actually optimal code, right? So they say this paper is more about, and they use the word ameliorations. We can help fix pathological code with like unnecessary instructions, for example. Another problem is it's not always obvious if we change the way the code works as we compile it because we're optimizing it. Have we preserved its correctness? Whatever you intended that code to do, if I'm going to modify the operation of the ultimate program that runs, I want to preserve what you intended the program to do. And a little bit fuzzy there. So the goal is to preserve side effects, do whatever the code did, eliminate common mistakes. So that's what this paper's about, common mistakes. And here's the structure. They say, first we'll talk intra-procedural optimizations. That's where I've got procedure A calls procedure B. And she sort of says that elsewhere, this is like the hardest thing to do. Then there's transformations best performed on a program form close to the source language. Then you get so-called, she says so-called in quotes, machine-independent optimizations. It's almost like there's a little bit of skepticism that any optimization truly is machine-independent, but we'll call these machine-independent. And then finally, machine-dependent optimizations. And in keeping with my interest falls off a cliff when we get to the back end. Number 4, I'm like, I could just skim this part, right?
It's the best part, Erik.
Well, so I mean, if you think what's machine independent, what's machine dependent, you could say, well, that example we gave before where I'm assigning to a variable inside a loop. It's really wasteful if it doesn't relate to the logic of the loop, I can move it outside. That's an unnecessary instruction. Right? I can do something a little more efficient. The same type of efficiency we'd look for when refactoring code, maybe for readability or simplicity or whatever. We reduce instructions, and that'll help any machine. But then machine dependent stuff is like, how many registers do I have and how am I going to use them? And you're telling me you're interested in that part?
Yeah, I had never even actually thought of this, but it's kind of fascinating to me that, they do this analysis on the program. And if you have programmed in assembly language or directly in machine code, you know that generally you have to pull stuff into registers to do operations on it. It depends a little bit on the CPU architecture. There are some instruction sets that allows you to sort of operate directly on memory, but generally speaking, you have to take variables and put them into registers to be able to do the basic CPU level instructions on them. And so this idea of trying to figure out what things to put in the registers to make the computations happen in the optimal order and so forth is kind of interesting to me.
It's interesting that it exists. I don't want to go in that. I want to write programs that run on the minds of ghosts. I don't care about registers.
Well, I think so. My take on why she sort of quotes this, or she has the so-called thing in there about machine
So-called machine independent optimization. A little bit of skepticism there.
So if you think about some of these things that we're talking about here, like you were saying, a lot of these will end up eliminating redundant instructions. Even there, you have to know, this is all boiling down to machine level instructions. So you have to know a little bit about.
Do I, though? Do I?
Well, I agree that you do, but think of, so there's a technique called strength reduction, for instance.
Oh, we're going to get into them now. That's a machine independent, right?
That's a machine independent one. But, one of the consequences of strength reduction is that in some cases in the strength reduction optimization, what happens is that you end up replacing a multiplication with an addition. And so it's machine independent, but it requires you to know that addition is a less expensive operation on the hardware than multiplication is. So,
but I don't need to know that for a particular machine.
Yeah, you don't need to know it for an ARM CPU as opposed to an Intel CPU necessarily, but you do have to realize at some level that the bit level operations that are happening in the CPU are different for those two operations.
So I kind of want to skip over the interprocedural stuff a little bit. She has some breakdown of what it means. I've got a caller, I've got a callee, interprocedural. She says there's closed, semi-open, semi-closed, open. Some of these are harder than others. One of the problems is if you have a lot of side effects, this can get really hard. I kind of want to skip over that a little bit. So look up the paper if you want to know more about that interprocedural stuff. Here's the stuff I found cool. And again, we're talking compiler optimizations. And here's what's interesting about this paper. Almost all of these techniques are still widely in use. So they show up in 1976 and they become the tools that compiler writers use today. If you use a compiled language, chances are these techniques are present somewhere in the compiler. In addition to other techniques, sure, but they were invented by this person. Not all invented, but they were cataloged by this person who invented some of them in the 70s as part of her summer job, working at IBM. So the machine independent ones, I no surprise here, probably. I did find them a lot easier to kind of grasp. So I'm just going to read the names of them, and we'll kind of dive into the ones we find interesting. So there's loop transformations, which includes loop unrolling. I've definitely heard of that, unrolling loops, right? And then jamming, which I don't think I'd ever heard this term, or loop fusion, and unswitching, which is the opposite of jamming. I don't know why they call that unjamming. There's redundant sub-expression elimination, code motion, moving code around. By the way, code motion, Mike, that sounds like a really good name for our future reggae band, Code Motion.
There's got to be a company called that, right? Code Motion.
Code Motion. Well, there's going to be a reggae band, you and me. Anyway, there's also constant folding, dead code elimination. Definitely something I've heard about quite a lot. Strength reduction, which you mentioned. Linear function test replacement, and carries. All right. So which ones should we try to give a? I don't think we can't describe all of these, and some of them I don't understand. Let's take the ones that I have a chance of understanding.
Well, let's try loop transformations.
Okay. So jamming was pretty cool. Like if you have the exact same loop twice, right? I loop over a data structure and I do something. And then I loop over that same data structure and I do something. Well, you could really just loop once. You could do the two somethings in the body of the loop, right? That makes sense.
Yeah, it makes good sense. I encountered the loop unrolling in the early part of my career. So I think the basic idea of loop unrolling is that you're doing it's a loop, so you're doing some operation over and over again, and there are certain cases where you can just simply write the individual instructions rather than looping through them. The reason I encountered this is because when I was programming on Cray computers in the very early part of my career, they had actual instructions that were vectorized. So you would end up writing loops in such a way that you always wanted the inner loop to use the vectorized operation. So you would kind of like if you had a doubly nested loop, you would sort of unroll the inner loop so that it was using the vectorized instructions, which basically means that instead of doing say a multiplication or addition in a loop, you would have this single instruction that could do say 16 multiplications or 16 additions in one instruction. So it would had a huge performance impact.
And again, we're not talking about writing code like this. We're talking about a compiler that reads your code and says, oh, let me get my red pen out and fix this for this guy. That's rad. That is a rad idea.
Yeah.
So there's also redundant sub-expression elimination. This is where you find and you eliminate computations which calculate values that are already available. So it's like, I don't need to recalculate this thing over and over and over again. You can move code around. Sorry, go ahead. Sorry.
I know that also is common sub-expression elimination. So if you've heard that term, it's the same thing.
So code motion, that's our reggae band, that moves code around. So you can actually move it and end up with fewer instructions. So like assigning a constant value inside a loop, that's pointless. We probably wouldn't write code like that, but you might. And the compiler's like, I got you. Constant folding. So instead of looking up a variable, you could stuff a constant in there. This one kind of makes sense to me. Is this a Fortran specific thing? I mean, in Python, I'm always going to have like a pi object, right? It's a variable on the heap. Even an integer is going to be on the heap.
I don't think it's a Fortran specific thing, but it may not apply to all compiled languages.
Yeah, I mean, maybe Python's a good example, not a good example, because people say, well, this is interpreted. We didn't talk about interpreted versus compiled. I always find that distinction dissatisfying when people start describing it. My gut is, well, a compiled language is going to translate it into assembly, machine language, machine code. An interpreter is like, I'm going to write a program to parse and then evaluate expressions. And my program is interpreting this other program. I just said I don't want to do the distinction, and then I tried to do it. All right, moving on. Dead code elimination, something I've heard a lot. It's something that sounds awesome. You can find code that's not in use and just throw it away instead of compiling it into the resulting program. That's freaking rad. This was invented in 1976. It's awesome. Here's a line from the paper. Primarily as a result of constant folding, instructions become dead. I wonder if that's still the case because of constant folding. Instructions are considered dead when they cannot be executed because they are in an area of the program which cannot be reached, or when their results are never used. This happens when I write in my editor and it's like, you can't reach this chunk. And I'm like, oh, you're right, linter. I will delete that.
I was kind of hinting at this at the early part of the episode, but this has gotten me a couple of times over the years where you're trying to do maybe some benchmarking. So you write this loop that loops a billion times or something to see how long it takes, and then you run it with the optimizer on, and suddenly your program runs instantaneously.
Yeah.
It says you're not using the results. I'm just going to throw this away.
Yeah,
Uh,
you are benchmarking the compiler optimization successfulness. Okay, so strength reduction. That's the last one I wanted to do. We could do some of these other ones here, but strength reduction, I have a little bit of difficulty with it. You referenced it, so help me out. Here's what the paper says. The strength reduction optimization replaces certain computations using recursively defined variables by recursively defined computations. So if I've got variables that are like interdependent on each other in computations, that's the recursive part. They point at each other. I could change it to recursive computations, and that is actually a strength reduction. So that helps me. You gave an example of multiplication and addition, which made a lot more sense to me than this phrasing. I didn't understand this phrasing.
yeah, so there's a couple examples I came across. This apparently happens anytime that you are using, or can potentially happen every time that you are using the loop counter itself to calculate something. So, say you're doing like a 4, I get 0, I is less than 10, I plus plus type of thing. If somewhere inside that loop you calculate something which is like I times 5 plus n or something, that multiplication inside the loop is expensive. But a lot of times, if you think about what's happening there, is you're really just, since I is just incrementing by 1, what you're essentially doing there is you're just adding 5 to something every time you go through the loop. So what strength reduction would do in that case is it would create a temporary variable that's the same as I at the beginning, and it would just do an addition of 5 each time through the loop rather than doing that expensive multiplication. The example that I saw that involves the sort of recursive definition is, it's similar, but it's like in one branch you have like two variables I and j, and you take one branch where I is calculating something from j,
Mm-hmm,
and then you
mm-hmm.
take another branch where j is calculating something from I.
That's the recursively defined variables thing. Yeah, okay.
Right. That's another situation where you can sort of define temporary variables and turn what might be a multiplication into an addition.
Mm. So that's a strength reduction. Go from multiply to addition. Addition so much easier for the CPU to do.
Yeah, I think generally what's happening here is you're replacing an expensive operation with a less expensive operation.
That's why it's called strength reduction. Okay, all right, that helps me. I liked this paper, but I didn't come away reading it like, oh, I can actually implement any of these things. Like this dead code elimination is like 1 or 2 paragraphs, maybe 5, 6 sentences. It's like, oh, you can do this too. And I'm like, great. How do I do it? Draw the rest of the owl, Mike. The last part is machine dependent. And this is where I get pretty lost because I do have trouble holding registers in my head and thinking in terms of assembly. I've written a little bit just for education, right? And I was using I went through a course where they're using MIPS, so I couldn't even read the x86. I have no clue. So please take pity on me for that. Some of these include instruction scheduling, where you can move instructions around to take advantage of assigning values to registers, and then you have fewer instructions just by moving them around. Okay, I guess I buy that. Parsing methods didn't really follow. Register allocation, which she writes is quite possibly the hardest optimization to perform. Allocating registers. Storage and adjacency. This one kind of made sense to me, called storage mapping. You can actually decrease dead space. You can kind of push stuff closer together, right? And does it matter if the registers are near each other? That shouldn't matter, right? It should matter if the storage, the data we're accessing is closer in memory.
I think this must have to do with machines that have an alignment requirement. So some CPUs require that variables get aligned to the word boundaries.
Mm.
And so I've seen situations where you can move the way that storage is put into memory such that you don't end up with too many gaps.
Oh yeah,
So
yeah.
um,
That's
you
what is
know,
what they were talking about. Yeah.
yeah, I think on some CPUs, like I think some of the older Intel CPUs didn't have that word alignment, so this might not be such an issue. But I know that like the ARM CPUs do have a word alignment requirement, so you can sort of minimize the amount of unused memory you have by putting things in a particular order.
That sounds similar to what they're talking about. There's 4 more: shadow variables, anchor pointing, special case code generation, peephole, or window optimization. So shadow variables sounds like they were giving the example that there are decimal numbers that are easier to deal with as binary. So you can keep the originals, but you can make a copy in binary and do the computation on that copy. That's a shadow variable. Okay. Anchor pointing, this sounded a little bit like branching with early returns to me. I don't know why they called it anchor pointing. Maybe it sounds like jumps and go-tos type of thing. We're going to jump to this instruction. That's an optimization they can automatically perform sometimes. It's pretty cool. Special case code generation. This again similar to what you're talking about strength reduction. You could take like a squared and turn that into a times a and not use exponentiation. That might be an easier instruction. And then finally, peephole or window optimization. So you can actually take a window of instructions and optimize all of them together, which sounds like a mega draw the whole owl. Draw a bunch of owls now that you're good at drawing the owl.
I would guess this has probably gotten pretty complicated in modern CPUs too, because you want to make sure stuff is in the L1 cache, and a lot of the CPUs now do pipelining. So there's certain ways you can set up the computation so that the pipelining works better. And so,
what does that mean, pipelining? Like,
it's the ability of a CPU to essentially execute multiple instructions in one clock cycle. So there's a
so it's like hyper efficiently moving stuff in and out of registers. It knows what's coming next. Is that?
Yeah, and there's I think I remember reading somewhere where if you arrange the computation in a particular way, it assists the pipelining system in these things, so you can take advantage of the hardware. So I suspect a lot of I suspect this part has expanded a lot and also gotten hopelessly complicated.
Okay, so if you're like me, you write programs in a so-called high-level language. Most of our languages these days are languages that somebody would call a high-level language, even C, I guess. Then you might find this work interesting to know about. Comes in the 60s, from the 60s, 70s, early 80s. Francis Allen, papers we talked about, control flow analysis, catalog of optimizing transformations. And just to sum up, you can parse a program, build a graph out of it. You can analyze that graph to determine what knowledge, this is a metaphor, but what knowledge is available at each point in the graph. And with that analysis performed, you can then move on to optimizing the result. And you can actually just probably prune the graph. Like, well, let me move this node over here, and I'll change the instructions in this block over here, and I could actually delete this node entirely. This is rad. It's really cool stuff. You start with parsing a string, you end up with a graph, and then you end up with all kinds of cool cool optimizations that you run on top of the graph. I just find it fascinating.
It is, and I think another thing that's interesting to me is that you said this a couple of times, but this stuff is pretty much all still relevant to modern compilers too. In fact, a lot of it is built into the LLVM system, which is sort of this elaborate set of tools for building compilers. So if you look at the optimization passes in LLVM, you'll still see a lot of these terms referenced.
Yeah, and LLVM, so you can write, this is how Rust works, for example. You compile Rust into an LLVM intermediate representation, and then LLVM takes over and compiles into machine code. And LLVM does all of this cool optimization passes. Now, it does abstract us away a couple steps from, I'm writing this code in Rust. How is it actually going to be optimized when it gets run? There's a couple stages away from me and that endpoint, and it can get confusing. But on the other hand, I like writing Rust, and it's pretty rad that someone is out there eliminating my dead code and reducing the strength and making it faster. That's exciting stuff.
LLVM is low-level virtual machine, incidentally, just in case that's not familiar to you.
Well, Mike, I really enjoyed this topic today. I really enjoyed the paper control flow analysis. Thanks for bringing it. So this is the work of Francis Allen, and I recommend you go out and check it out. And check out the compiler optimizations that are in use today. Wikipedia has a page of, there's like 40 of them. And unlike half of them that are mentioned on that Wikipedia page, which talk about contemporary practices in compiler optimization, they're in this paper, a catalog of optimizing transformations. It's pretty cool to just reach into the past and see, hey, this is where that came from.
Yeah, it's inspiring.
This has been Picture Me Coding with Erik Aker and Mike Mull. Thanks so much, Mike. We'll see you next week.
See you next time.
Bye-bye.